Hey guys, so this is another day of solving programming problems. So today we're going to take a look at one of my favorite programming problems, just because the problem itself is a bit more practical, I think, because it has like physical properties in it. So the idea of this problem is to find the blocks of rainwaters that can trap and inside a brick-like structure. So that's the idea of the problem. So if you don't get it, I'll go further deep into what the problem is about and what we're supposed to find out. So I've just copied this image from Geeks for Geeks because I was like too tired to draw this out in whiteboard. So I'm just making use of this. So we are going to take an example array. So the array has values called 300204, right? So the idea is that the 3 signifies 3 blocks of brick on position 0, right? So the first position you have 3 blocks of bricks, and at the second position you don't have any blocks of bricks that are in like vertical position, not like it's not laid out on the ground, it's like up top, right? So and you have 0 blocks on the third position, and you have 2 blocks on the fourth position here, and you have 0 blocks here, and you have 4 bricks at the end of this. So the idea is that when it rains, how much of blocks of water can this structure hold is the question right now. So for example, here we have 3 blocks, right? And on the second position, you don't have any blocks. So you are able to store 3 blocks of water at the second position right here, and even at the third position, you're able to store 3 blocks of water because like at the left hand side you have 3 blocks like covering it, and at the right hand side you have like 4 blocks covering it. So even if the water rains, it'll hold up till that position. Because imagine if you'll not be able to store more than 3 water levels at this position, because if you go to 4, the water might just like flow out of this left hand side. So that's the idea here, and we're supposed to find the total trapped water within the structure. So the algorithm to solve this problem will make use of 2 arrays. One array will hold the maximum left part um, of the entire structure, and the other, what do I mean by that? So I'll go into that a bit detailed. So the other array will hold the maximum right part for the whole structure. So the idea is that at any position in the structure, what is the maximum leftmost tallest block level that we are going to store in the maximum left block. So for example, the maximum left at position 2 will hold the tallest structure that's leftmost to the second position. So in this case, we have 0, 1, 2, right? So we have 0 here, and the tallest structure that's on the leftmost from the position 3 is this 3 blocks. Uh, Not smallest, the largest, right? So the largest is this 3 blocks. So even if we take this position here, the one before the last, we have 2 blocks and 3 blocks, but the largest is this 3 blocks. So we will be storing 3 at this position here. So that's the idea behind left and right. So similarly for right, we are going to store the rightmost tallest element. So in this case, even if we take the position 2 here, the rightmost tallest element is the last one here, because it has like 4 blocks, and the one before it has like 2 blocks in it, so we are going to take the maximum one. So the idea is to have these 2 arrays within us, and once we have these 2 arrays, what we need to do is that we need to iterate again through all these 6 elements, and we need to find the minimum of left and right, and then subtract it from the position that we are iterating in. So for example, we have 300204 here, right? So what we need to do during the first iteration, what we would do is that we would check both these arrays, and we would find the minimum elements at both these positions. So for example, probably the leftmost would contain 3 here, I guess, right? So 3 is the maximum here, and the rightmost position uh, at this place, maximum position is this large block of 4. So that's the largest, so 4. So the idea here is that we would find the minimum of both these elements. So minimum is 3, and we would subtract it with the element at this position, which is 3 again. So 3 that we are getting it from here, this would come up to here, and this 3 we are finding it from the minimum of both these positions, right? So and then we would add it to a total trapped water variable. So right now we have 0. Likewise, we would take for the first position, what is the leftmost tallest, right? So leftmost tallest is again the 3 because we have no other blocks, and the rightmost tallest is 4 because we have there's nothing more taller than the 4 blocks here. So we would find a minimum of both these two. Again, it's 3. We would put 3 here, and we're supposed to subtract it from the first index position, so 0, right? So subtracting it with 0, we get 3. So we're able to hold 3 levels of water at this position. So that's what we are able to find. So even here, like we're able to like hold in 3 elements, right? So similarly, we would iterate it for the entire array, and then we would find the total amount of trapped water that we could hold. So that's it for the algorithm. It's pretty straightforward. We will just have 3 iterations, not like in nested, but like on one by one. And by the end of the third iteration, we'll have the answer for this problem. So I'm gonna code this in Java just because like I like using Java. So as I told you before, we will have 3 variables that are holding. So left max, which is going to be, wait, it's still, I don't know if the syntax is right for this one, but we'll go with this. Int right max new end of size n, because n is the length of the array. And then what else do I need? Yeah, the total water capacity, I guess. I'm just going to set it to 0 initially. Then we are going to do 3 iterations. So the first iteration, we'll try to find the left max. Yeah, so I'm gonna before we do that, I think it's better to set the first element of left max because we know the first element is going to be the first position in the array. So the left max of 0 would be the array at index 0, right? So, and then we could start iterating from 1. So I is less than n and I plus plus, right? So this is our iteration, and we are supposed to save I by figuring out the math dot maximum of left left max of the elements that we figured out so far. So in this case, it would be I minus 1. So that's why one of the reasons why we did why we set the value of 0, just because we wanted to reference that value. Because if we had iteration 1, we would need the value of 0 here initially for the first iteration. So that's why we said that. So we need to figure out the maximum of the elements that we've figured out so far and the maximum of the current element. So that is the idea here. I mean, you could even make this a bit more cleaner and remove these curly braces because we don't need them. This is one line. Anyway, so for the next, we need to figure out the right max element. So before we do that, we need to set the rightmost element. So the element at position n minus 1 would be equal to the element at position n minus 1 here. So the last right max will be the last position of the array because you don't have any more elements that are righter than the rightmost element in a sense. So we are going to set that, and we're going to iterate through the array. We're going to start from the uh, element that's before the last element, right? Because we've already went through the whole process of getting n minus 1. We need to start from n minus 2. And the condition is that it is greater than or equal to 0 and I minus minus. So, and similar to what we did with left max, we need to do the same thing for right max. The only difference is left max, right max of what do we need to do here? So the right max of I minus, is it minus one? Um, I think it's I plus one because we need to check the previous element, previous element in the sense that the next element. So we're going in backward direction here. We need to check that and the array element at I right now. So that should be it. Um, I'm missing something. Feel like I'm missing something here. Should be good. Yeah. So anyway, we figured out left max and right max. So the last iteration that we need to do is in order to find the total water capacity. So for that, we're gonna do an iteration from zeroth element to a regular iteration, right? So we're not gonna do anything fancy here. We are going to iterate through that, and then what we are going to do is that we are going to sum up total water capacity being plus equal to uh, math dot min of the left and the right max elements. So left max of I, comma right max of I, and then oops, and then subtract it with the index that we're in right now because we wanted to subtract the blocks that are in at that position with the minimum of left and right max. So once we do that, wait, oh, we need to set this as long. I didn't realize that we need to set that as long, but okay. Anyways, so once we do that, we are just going to return total water capacity. Yep. So I'm gonna compile this and see if it runs without any issues. Yep. Uh, Usually the initial compilation won't show many issues, but when you actually go ahead and submit it, there'll be a lot more issues. Um, Yep, so as you can see, I've already attempted this problem, but like it's pretty straightforward, guys. You just need to find the left max elements of the current position for every element that we're iterating through. We need to find the right max element of every position that we're finding through, and then we need to find the minimum of that so that we get the water level, and then we need to subtract the current element so that we can subtract the current element in the sense that if we had, oops, you know, okay, this is weird, but like if we had a block here, like one block here, and if we found out the minimum element is 3, right? So we get the 3 and we need to subtract this one block that will be stored here. So we need to do that as well, right? So we get 3 and then we subtract it with just this 1. So that's the idea behind subtracting the element at position 1 here. So that is it for today, guys. So it's pretty straightforward. So see you again tomorrow for the next problem.